Saxon Math Course 2, we're looking at Lesson 16, where we're going to be talking about U.S. customary system of measurement and function tables. So this first example is going to require us to know a little bit about units of weight. And so we have some information here. We're talking about 16 ounces is 1 pound and 2,000 pounds is equal to a ton. There are a few other things that we should probably keep in mind, but for right now, let's just hold on to these. And so this will be customary U.S. equivalents. What this is meaning is that we use this type of measurement in the United States. In most other countries, they use the metric system. So they're talking about kilograms, grams, as opposed to ounces, pounds, and tons. Okay, so with that in mind, let's take a look. Here's example 1. Suppose a pickup truck can carry a load of 1/2 of a ton. How many pounds can the pickup truck carry? So ultimately the question is, if we have 1/2 ton, how many pounds is that equal to, right? And so we're going to use this information up here. We see that 2,000 pounds is equal to 1 full ton. If 2,000 pounds is equal to 1 full ton, then 1/2 of a ton has to be half of 2,000 pounds. Half of 2,000 pounds is 1,000, and that's how we'll get our answer. Here we have an example 2, another set of customary, U.S. units in terms of length. When we have 12 inches, that's 1 foot, 3 feet, that's 1 yard, 1,760 yards is 1 mile, and 5,280 feet is also 1 mile. The question we have here is 1 yard is equal to how many inches? Well, let's think about it. If I have 1 yard, I know, let's see what information I have about 1 yard. It's equal to 3 feet. And if 1 yard is equal to 3 feet, and I know that in each of these feet, I have 12 inches. So there's 12 inches per foot. So there's 12 inches and then another 12 inches and another 12 inches because I've got 3 feet here. I can add that up or multiply by 3 and recognize that 1 yard is equal to 36 inches. This next example is asking us to do something that we're not always used to doing in math, where we kind of are guesstimating, estimating, using the smartest way of thinking approach. A mountain bicycle is about how many feet long? So now you got to think about a mountain bike, and you got to think about what you've seen and how you would estimate its length. So if you think about a bike, and it's a mountain bike for an adult, you'd have to think, well, the wheels are kind of large, and maybe they're about 2.5, maybe 3 feet long, maybe 2.5 feet wide, something like that, 2.5 feet. So that already gets us 2.5 and 2.5, and then there's some more space here. And if we think about the handlebars, please don't laugh at my bike. This is starting to look like a bad pair of glasses with antennas coming out of the side. But anyway, we'll make it look like a bike. We can do it. If I do that, now it's a bicycle, right? So if you think about it, if you think about how, make it like a tire. I'm sorry, now I'm going too far. But if you think about how long it would be somewhere past 4, 5, maybe even 6 feet long if we think about that space in between, right? From here to here. So one thing you want to be able to do when you understand measurement is you want to start to be able to eyeball or visualize the lengths of things as you see it in reference to particular units, whether it's inches, yards, feet, or whatever. So here we're going to talk a little bit more about different customary units that we use in the United States. We're now talking about probably one of the more confusing things for me or hard to remember, but I'm going to give you a little new device to help you remember. So it's going to be kind of cool. If I've given it to you before, just accept it and just take it double time. It's going to be awesome. So we've got gallons and we've got quarts and pints, and they're all kind of related together. I'm going to draw a picture that we're going to talk about to help us remember this and to keep it in mind. So I'm going to slide this up real quick, and I'm going to pick out a marker, and I want you to know the big G stands for gallon. And inside every gallon, there are 4 quarts. I don't know if I like the way those quarts are looking. They're about to be quarts, you'll see, because I'll put Q's here. So inside every big G is 4 Q's. I even think that this is so cool, you should copy it down. So gallon contains 4 quarts. Each quart contains 2 pints. All right. So each quart contains 2 pints. Let's see, pints are going to be orange here. So a pint and a pint. And I'm just going to have 2 pints. So now what I can see is the relationship that 1 gallon actually has 8 pints in it. And so now inside of each pint, we are going to recognize that we have 2 cups. The yellow is not a great color. Let's try just black, whatever. We've got 2 cups. So I'm going to put CC in each of these. Just rocking a little CC all the way around, all the way around. That's a C. So we've got 2 cups in each of these. Make sure you're writing this down because it's mad helpful to hold on to. And inside each cup, you have 8 ounces. All right, OZ is the abbreviation we use for ounces. So this is the information that they're talking about here. That's all of this is written here in a relatable way. 4 quarts in 1 gallon, 2 pints in 1 quart, 2 cups in 1 pint, and 8 ounces in 1 cup. So I like being able to look at it and it helps me go through problems. So let's go ahead and do just that. Let's go through some problems here. So we're dealing with Steve. Steve drinks at least 8 cups of water every day. How many quarts of water does he drink in a day? So we know 8 cups of water is how much Steve drinks. And with that 8 cups of water, we can think about it as, since we know that there are, well, let me think. Let's go back to our little thing up here. Since we know that within each quart, there are 4 cups. Within each quart, there are 4 cups. We can consider how many quarts we have given the fact that we have 8 cups. So 4 cups, just from our picture, 4 cups makes 1 quart. Therefore, 8 cups, hopefully this is making sense, 8 cups makes 2 quarts. So the answer is 2 quarts. For this next example, we're going to have to keep 2 very important numbers in mind when we're dealing with the Fahrenheit scale, also another American preference. We're going to consider that the temperature where water boils is 212 degrees Fahrenheit and where water freezes is 32 degrees Fahrenheit. So we're going to calculate this. No, you can see the answer, but that's okay. We'll see how to do it. It says how many degrees are between freezing and boiling point of water. We're going to take 212 and we'll subtract 32 to get 180 degrees. So here in example 6, we're like turning the whole table over and we're thinking about something different. We're talking about function. And function is a little bit, it's not hard to explain, but it's a little weird to talk about it in some context, because it's like, what is a function? But let me just see if I can give you a picture of what a function is. So if you had a machine, right, this imaginary machine, where when you dropped one number in, something happened to it, that's your input, and then you got an output. And if for every input, there's only one output, and so if I put a 2 into the machine, let's say I get a 4 out. If I put a 4 into the machine, I get an 8 out. If I put a 6 into the machine, I get a 12 out. You probably know what I'm doing already, right? But this is an example of a function. A function is a relationship, which we're showing as a machine, where it maps or it pairs 2 numbers together. It pairs 1 or 2 numbers together. Something like pairs two numbers together. Let's say that. So in this case, we could write the input and the output in a table form. And that's what this is going to be up here. So remember what I said? I said 2 went in, 4 came out,
I don't know what I did. Maybe 3 went in, 6 came out. So I do 3, 6. So input and output. So in-out table is sometimes what these are called. And then the question is, what is this machine doing? What is the function here? And what we're going to do is look at the relationship. Really look carefully. If I put 4 in, 8 comes out. If I put -3 in, -6 comes out. So what's the relationship? Well, if you think about it, the relationship is 2 times the in is equal to the out. All right? Take a moment to think about that before we get started on the next, on this example.
Okay, so let's see what our job is here. In this table, we have the weight in ounces for a given pound. So the relationship here is that if I have 1 pound, that's 16 ounces, 2 pounds, that's 32 ounces, 3 pounds, 48, 4 pounds, 64, and so forth and so on. The question that we have to do is to determine what the relationship here is between these two things. So what do I do with the input in order to get the output? So this table gives this weight, and we want to know what the output's going to be. So as I look at this, it looks like for each input, we already know that for each pound we have 16 ounces. So if I were to take the input and multiply it by 16, it gives me the output. The way this would be written in terms of like an equation would be X and Y. So you could look at this as 16 times X is equal to Y. We're getting a little ahead of ourselves, but let's take a look. So that's describing the rule of the function. This next part is asking us in part B, if Maddie weighed 7 pounds when she was born, use the function rule to find out how many ounces Maddie weighed when she was born. So already you remember our functions down here, our relationship. If we n times 16, that's what that means. Or we had X times 16 equals Y, the output. And the X again stood for pounds. And the Y over here stands for ounces. So how would we do this in this situation? We would say, well, if she's 7 pounds, we know we multiply 7 times 16. If she's 7 pounds, multiplying 7 times 16, we're going to get, what is that, 112? If my math is correct, we should get 112 ounces. Not do OZ. Let's see, does that make sense? Yeah, it does. All right, we have another example. Let's look at example 7. So we have Hannah in example 7 who bought 4 yards of fabric to make a costume for a school play. Make a function table that shows the number of feet, that's the output, for a given number of yards, that's the input. Use the table to find the number of feet of fabric that Hannah bought. Okay, so let's go ahead and get started. Our input and our output have defined characteristics. We're told that our input is going to be the yards, so I'll put that here, and then our output would be the number of feet. So the first thing, we're going to make a function table that shows the number of feet output for a given number of yards. So let's try it. If I have 1 yard, that's pretty easy. That's going to be 3 feet. I'll leave the units off of that. I'll just put 3 since we know that's street. If I have 2 yards, that's going to be, can you think of it? 6 feet, yep. If I have 3 yards, that'll be 9 feet. So I have this relationship. If I think about the relationship, it's pretty clear that if I take the input and then I multiply the input by 3, I'll get the output. That's my rule. If I call the input X and my output Y, I could write this as 3 times X is equal to Y. With that in mind, we know that Hannah bought fabric for a costume play. She bought 4 yards. There it is. So I know that 3 times 4 is going to give me my Y value. 3 times 4 is 12. We recognize that for an input of 4, we get 12 as an output. And that is it. So now that we have that going on, what we're going to do is spend some time on the practice set. And as usual, I want you to do the odd problems in the written practice and make sure you read through the even ones, because we know that those even ones are fair game for tests. All right, talk to you soon. Take care and bye-bye. Here we are at Saxon Math Course 2. We're going to be talking about Lesson 17, which is measuring angles with a protractor. So it would be good to have a protractor, but we'll see what we can do in the video to kind of simulate having a protractor. So here we have what amounts to a protractor. And so a protractor is a semicircular, oftentimes it's a semicircular tool that's used to show what an angle is measuring or how wide an angle is opened. So we already know how to refer to angles. So let's talk about the measure of angle AOB. And I know it's at the bottom of your screen, but let's think about how we got to 30 degrees. Angle AOB is here. Let me use a highlighter to focus our attention on this angle. A couple things that we want to show. Protractors are generally clear. So if it's clear, you can take your protractor and literally lay it upon the angle that you have. If you lay it upon the angle, you want one side of the angle to pass through the 0 mark. I know that there's a 0 here. There's a 0 here as well. Put it near to the most convenient 0, one side, and then make sure that the angle opens up to the other side, and it's also being measured with your protractor. So from 0 to 30, we can see that's the opening there. So we can say with some sort of confidence that angle AOB is 30 degrees. If we turn our attention from angle AOB and we thought about, let's say, angle AOC, so I'm going to highlight that one in pink, we would do literally the same thing. Because one side is already passing through the 0, we're just going to focus our eyes on the place where the 0 starts. Notice we didn't call this 150 degrees when we were measuring the green angle, angle AOB. We started from 0, 10, 20, 30, just like you would if you were counting up. We open up and count up in the same way. This pink angle, this angle AOC, is larger. So when we have the measure of angle AOC, we know it's going to be greater than that 30 degrees. We're going to count open 0, 10, 20, 30, keep going, 40, 50, 60, 70, 80, 90, 100, 110. So the measure of angle AOC is 110 degrees. If we go even further and we open up even wider and we get to angle AOD, we can see that starting at 0, we just start counting all the way up. We get to 150 degrees. So the measure of angle AOD is 150 degrees. If you have a protractor home, that will be the best way to complete some of the questions in this assignment. Let's go ahead and take a look at some examples. So let's see what we have going on here. I kind of like the idea of highlighting my angles, so I'm going to do that again. So we're looking to find the measure of angle AOB. So we've got AOB here. Again, we want to look where we're starting. We're starting at 0, 10, 20, 30, 40. But it's between the 40 and the 50. If we were to zoom in just a bit, let's see where that's going. Between 40 and 50, 45. 1, 2, 3, 4, 5, 45 degrees. So I'm feeling pretty confident to say that the measure, I'm going to put a little M back here because that's what that means. The measure of angle AOB is 45 degrees. Let's try another one. So if I'm looking at this angle over here, how about angle AOD? I'm going to start here with A, get to O, and now the ray that's going to be the terminal side or the ending side of my angle will be OD. Now some kids who are not paying attention say, oh, all I got to do is look at this number, and they'll say, ooh, it's 40. That's just 40. It's not. Because remember, we start at the beginning. We call this the initial ray, and we open up all the way till we get to the terminal ray. 0, 10, 20, 30, 140. It's actually at 140. 140 degrees is the measure of angle AOD. And finally, we get to the measure of angle
EOD. EOD is kind of interesting because none of these rays that make up EOD pass through the same zero value over here, but it does pass through zero on this side. So we're going to count up. I hope that makes sense. So if we start here, 0, 10, 20, 30, 40, EOD is 40 degrees because of the way we're measuring it, and we're measuring from zero and seeing how far open we are when we measure that angle. So in example 2, we're asked to use a protractor to draw an angle that is 60 degrees. What you want to do when you have this is get your protractor and first draw one straight ray that is a horizontal line, and you're going to call this the vertex of your angle. Make sure it's at the little dot or the little hole at the bottom of your protractor. I wanted to pull up some pictures of protractors so you can get an idea what I mean. Right here, we have the hole where you would measure where you would place the vertex of your angle right here, or that little corner or elbow joint in your protractor. That's the hole right there. Here, this is a double-sided one. That's the hole where you put your vertex. Right here is where you put your vertex. If you're a teacher and you had a big giant one, you'd put your vertex as close to that zero value there. That's where you put your vertex. You see, so sometimes it could be actually a little hole. Sometimes it can be a point that points to it. That's how you're going to use your protractor. So after you draw that initial line, you're going to line up your protractor like that. And then outside of your protractor on your paper, you're going to put a little dot where there's 60 degrees. So 0, 10, 20, 30, 40, 50, 60. You don't want the 60 that's kind of on this side. There's another 60 over here in case you are opening it up this way. You want the 60 there. You're going to draw your line straight through. And that's you drawing a 60-degree angle. And lucky for you, that's all you're going to need in order to complete the practice set, and also to work on the written practice odds when reading over the evens to answer any questions. So that's all we have for this lesson, lesson 17. Here in lesson 18, we're going to talk about, this is Saxon Math Course 2. Here in lesson 18, we're going to talk about polygons and the idea of things that are similar and congruent. So typically we talk about the word polygon as shapes. So polygon means many angles, and poly means many, and polygon comes from the idea, or from ancient Greek, where it means many angles, and so a polygon has many angles. So I don't like using the word shapes for polygons because lots of things have shape. A circle is a shape, but it's not a polygon because it has no angles, all right? So polygons, let's just go over this really quickly. A triangle has 3 sides. You might say square or rectangle, and those words are true. There is a square or rectangle that you could use for a 4-sided figure, but all 4-sided figures, whether it's a square, rectangle, parallelograms, nothing at all, a kite, all of the things, whatever we have a 4-sided figure, we call that a quadrilateral. 5-sided figure, pentagon. A 6-sided figure is a hexagon. I use that relationship to help myself keep focused about that because sometimes I get hexagon confused. A heptagon is a 7-sided figure. There's another word, septagon, sometimes it's used. An octagon is an 8-sided figure. Nonagon is a 9-sided figure. Decagon is a 10-sided figure. Undecagon, 11-sided, and dodecagon is a 12-sided figure. So after we get beyond those numbers, there are names, and they're not common for typical people to know, or it's kind of inconvenient. If we had a 15-sided figure, we'd say a 15gon. If I had a 12-sided figure, sometimes I call it a 12gon, even though it has the name dodecagon. So this is something that we ought to know. Let's go ahead and see if we can look at some examples. So here in this example, we have this figure and we're to name the polygon. This polygon, the best way to name it is to count the number of sides. 1, 2, 3, 4, 5. Let me see. 1, 2, 3, 4, 5. Counted it twice. I think that's nice. If it's a 5-sided polygon or a 5-gon, we know that that is a pentagon. So the first part is good to go. It's a pentagon. Now this next part is really interesting because it requires us to know the definition of what a regular polygon is. So a regular polygon has all the angles and all the sides the same length. So for instance, I'm going to make a little thought bubble. A regular polygon would be a square. Beautiful square would be a regular polygon because all of these angles are the same length or same measure, that's 90 degrees, and all of the sides, let's say they were 4 inches long, would be the same. But an irregular polygon, let's say an irregular quadrilateral, would be one where that's not the case, where all the sides are not equal in length and all the angles are not the same. That doesn't even look like a side, it look like a little crookedy thing. Okay, so this would be an irregular quadrilateral. So is this a regular or an irregular pentagon? And I hope you notice that it is definitely irregular because all the sides are not equal, nor are all the angles equivalent. Example 2 is asking us to figure out which of these figures is a polygon, and there's only one. A is not a polygon because it doesn't really have all straight sides. B is not a polygon because it's not a closed figure. It's kind of like just opened up. C is a polygon because it's a two-dimensional figure there. It's flat, it's closed up, all the sides are straight. And D is not a polygon. This is a three-dimensional figure, and that doesn't work for a polygon. In mathematics, when we talk about things being similar, what we're talking about is them actually having the same exact shape, but maybe being bigger or smaller. So when I'm talking about similarity, I'm talking about literally having the same shape. So I'm going to try and see if I can draw a similar polygon here. So I've got this polygon and make it look a little bit better. This polygon, and then I'm going to talk about this polygon down here. And these two polygons are said to be similar. Even if I were to turn it around a little bit, let's see, can I turn it around? No, let's not try to be fancy. Don't try to do too much now. Let's see. There it is. Okay, these two polygons are still similar because really, even though I rotated it, one side is similar to another side. It's like one got bigger, but everything else stayed intact in terms of the dimensions. With that in mind, let's answer the question. Which of these quadrilaterals appears to be similar? Appears to have the same exact shape, even if the sizes aren't the same. Which of the quadrilaterals seem to be similar? So to me, I'm looking at these guys, and this is clearly not a rectangle. This one is called a trapezoid. But these three rectangles look similar to me. However, I know what the textbook is doing. The textbook has similar and it has congruent. And so I know that 1 and 2 are similar. And I know that 4 and 2 can be considered similar pairs. Technically, all of them are similar, 1, 2, and 4, but since similarity is what we want, I'm going to use the ones that are definitely similar and not congruent. And when we talk about congruent shapes rather, we are talking about shapes that are exactly the same. So this shape that I'm dragging up here, these guys are congruent. Doesn't matter how I turn it, they're exactly the same size. Basically, when I think about congruence, there is a way for me to lay them directly on top of each other so that I can hide the one underneath perfectly. That's what congruence means. And when I see that number 1, and this guy, number 4, are definitely congruent. Hope that made sense. All right, so we've got congruence, similarity, those guys are similar, and these guys over here are congruent. So order matters when we name our shapes, our polygons. So which angle in angle XYZ corresponds to angle A in ABC? So we're going to assume that these two triangles are congruent, and we're looking at angle A, and we want to know which one of these angles here, X, Y, or Z, corresponds to angle A. And the cool thing is that we can look at it and see that A and X are kind of corresponding. So angle X is the answer there for part A. But you can also tell by the way the angle is named. If I name it XYZ and I name this one ABC, I name it according to its similarity. So the fact that A is first and X is first, it lets me know that those angles are going to be corresponding. They're the equal angles of two similar triangles. Let's look at part B. Part B is asking us which side of XYZ corresponds to BC. This actually has the same idea. Look at this. BC is here. YZ is here. Let's look at the picture. BC is this long side. YZ is this long side. So we can see that BC corresponds to YZ. BC corresponds to YZ.
You are all ready to do practice set 18, and you're all ready to get started with the written. Do the odd ones, read the even ones, because they're fair game for the test. All right, have an excellent one, and take care, my friend. Bye-bye.